Hello everyone. Here we'll discuss about fluid dynamics. In fluid kinematics, we were dealing with the velocity and acceleration of flow, that is mostly the moving patterns and geometry of fluid motion. But in fluid dynamics, we'll also take into account the forces affecting the fluid motion. So it can be expressed using an equation of motion, which is based on the Newton's second law, that is rate of change of momentum in a given direction is equal to the net forces acting in that direction, which is also written in this form, F equals ma. Here F, that is the net force, is the summation of all the forces, which will be the algebraic sum because we have to give either positive or negative sign based on the direction of the force. So therefore we can write it as net force equals the rate of change of momentum, which also can be written as mass multiplied by acceleration. So what are the forces acting on a fluid? So the forces we can classify as body force, which is, in case of the planet Earth, it is gravity force, but if you put some kind of fluid which is affected by some other forces, that is either electromagnetic forces or magnetic forces and some kind of force, so in that case that would be the body force. In most cases that we are dealing with, the body force is the gravity force, or that is the weight of the fluid. Then comes the pressure force, then viscous force, and elastic force or force due to compressibility. That is, if something is compressible and once it is compressed, it will try to expand back, so that is giving some amount of force, which is the elastic force. It's just like stretching a ribbon, and that will give a reactionary force which will try to shrink it back. So similar thing will happen in case of fluid also, if the fluid is compressible. Then if we consider all these forces, then the equation of motion that results from all this is called the Navier-Stokes equation. It's a very long equation actually. It's a set of equations. So it's a combination of the continuity equation combined with this momentum equation, or the moment that deals with the force. But that we'll discuss sometime later, but we'll only study a simplified form of the Navier-Stokes equation, which is called the Eulers equation. So Eulers equation can be obtained if out of the four forces that we listed earlier, that is body force, pressure force, viscous force, and elastic force, if viscous and elastic forces are ignored, then for steady flow, the resulting equation is called Eulers equation. So if we start from the first principle, that is from the definition itself, rate of change of momentum is pressure force plus gravity force. Then mass into acceleration is given by Fp, which is pressure force, and Fg, which is gravity force. Now let's try to discuss how we evaluate these forces and this rate of change of momentum. So for that, we'll have to consider some very small element. So let us consider a small element of stream tube having length of ds and cross-sectional area dA. So it will be like this. So this length is ds, then the cross-sectional area, this area and this area is dA. Therefore the mass of the element will be density multiplied by the volume. The volume of this stream tube will be ds multiplied by the cross-sectional area. So therefore dA into ds, we multiply that with density to get the mass of the element. Now this small element is making an angle theta with a vertical direction. So let's try to find out the forces acting on this. So let's put the diagram here. So pressure on the upstream cross section is taken as P. That is, this is the upstream cross section. Upstream means the direction from which water is flowing, and downstream means the direction to which water is flowing or any fluid is flowing. So here let's put the direction. This is the flow direction. Now, so pressure force at this cross section is pressure P multiplied by the area dA, that is P into dA. Now, as we have moved to this location, the pressure may have changed. So how much it will change will depend on the rate of change of pressure along this S direction. So that will be del P by del S. And since the length is ds, so therefore the pressure at this point, at this cross section, will be the original pressure at this cross section plus this little bit of something. This little bit of something is the rate at which the pressure will change per unit length, that is del P by del S, multiplied by the length, which is ds. So this is your pressure at this cross section, and therefore pressure force at this cross section will be simply this whole quantity multiplied by the area dA. So we have pressure force at two cross sections, and on the circumference of the stream tube we are not considering these forces, because since we have already mentioned this is a stream tube, that means there is no force, no flow across these walls, because the walls themselves are made of streamlines. Therefore the flow must be parallel to the walls, and therefore the pressure on the wall will not affect the flow. So we are considering the pressure forces only on the cross sections. Now the weight of the element, now we are talking about the gravity force. So the weight of the element is rho multiplied by g multiplied by the volume of the element, which is dA into ds. Now since we are talking about the S direction, that is this direction, therefore we have to take the component of this along the S direction. Now if we take this as the positive direction of S, then we'll have to see what will be its component, that is component of this weight in that direction, and that will be this much. So this is in the opposite direction of S, so therefore we'll have to write this negative sign, so minus rho g dA ds cos theta. Cos theta because we are taking the component along that direction. Now the equation can be written as ma equal to F, that is rate of change of momentum, is equal to the force. So rho into dA into ds into A, that is dA into ds is the volume, that multiplied by the density is mass, multiplied by A is, where A is acceleration. So this is ma. This whole term is equal to m, and this is A. Then we, on the other side, we put all the forces. This is pressure force on the upstream section, this is pressure force on the downstream section, downstream cross section, and it has a minus sign because the directions are opposite, and this is the component of weight of the element, and here also there is the minus sign, that as we have explained previously. Now this A we can write as dV by dt, therefore we have replaced it with dV by dt. Now since we have learned in kinematics that dv by dt is the material derivative or the total derivative of velocity, which can be expanded as del v by del t, which is the partial derivative of velocity with respect to time, and this is the convective acceleration, which in the continuity equation, in the acceleration term, material derivative, it used to be the summation of u del u by del x plus v del u by del y plus w del u by del z, and similarly for other directions also. But here the direction is only one, because we are not considering velocities or accelerations in x, y and z directions. We are considering velocity in the s direction, that is the direction of the stream tube. So therefore we are writing only one term where v is the velocity in s direction and del s is del v by del s is the rate of change of velocity along that s direction, and that equals, all these terms are just same. Now for steady flow, this term del v by del t, that is rate of change of velocity at a given point without moving that point, that is with time, will be 0. If it is steady flow, that is del v by del t equal to 0, and we can write it as rho del dA into ds, v del v by del s. Then we can expand this second term, which will give us minus p dA and minus del v by del s ds dA, and the last term we can write as, you see, these and these are remaining the same, but the cos theta is replaced with dz by ds. Now what does that mean? Let's try to understand with the figure again. So this is the length ds, and z is just the vertical direction, vertical dimension. So therefore, if this is the length ds, then dz is the vertical component of that length, and dz by ds will give us cos theta. So therefore we have replaced cos theta with dz by ds, del z by del s. We could have written dz by ds also, but at the last step it creates some confusion, so I replaced it with del z by del s, and it would mean the same thing, because z is, in this case, since z is not changing with respect to other dimensions, therefore del z by del s and dz by ds should mean the same thing, because we are not exactly concerned about the other dimensions x and y. Now here this term and this term gets cancelled, and if we divide this whole term, whole equation by dA ds, then from all these terms this term gets cancelled and we are left with a much simplified equation like this, and again dividing it by rho into del s, we get this equation. Now we have divided it by rho and multiplied with del s, so we'll get this equation. Now we can just shift things to the left hand side of the equal sign, and we are left with this final form, which is called the Eulers equation. Now this Eulers equation is also, it is useful, although it is useful, it's difficult to use in real calculations because it's a differential equation. So we want to get some algebraical form, and to get that we need to integrate it. By integrating we can get some other form of this equation, which is called the Bernoullis equation. So in Bernoullis equation, we simply integrate the Eulers equation, that is this one, and by integrating we get a constant on the right hand side, because integration of 0 would be a constant, and after that we'll get this form of the equation. Here it is difficult to make sense of all these terms physically, so what we do is we divide everything by g. Then we get p by rho g plus v square by 2g plus z equals a constant. So this is called the Bernoullis equation. Now let's try to understand what this equation means. So it can be stated in sentence form as the sum of various forms of energy in an ideal, that is inviscid. By ideal we mean the flow where the effect of viscosity is neglected, then steady flow and incompressible flow, because we've already ignored the viscous forces and the elastic forces, and we've also assumed that it is going to be a steady flow because at some stage in the derivation process we assume del v by del t equals 0. So in that case, the sum of various forms of energy in the flow remains constant throughout the flow field. Now what does that mean is, let's try to imagine a pipe. That is, a pipe has a variable cross section. So at this cross section, whatever was the velocity will increase when the fluid reaches this cross section, because this cross section is smaller, and to satisfy the continuity equation, velocity has to increase. If velocity increases, that means the kinetic energy also increases. So this equation, which says that the summation of all these terms remains constant, that means if we find the summation of all these terms at this section 1, which is p1 by rho g plus v1 square by 2g plus z1, whatever that summation value is, if we calculate the same summation in this section, section 2, that is p2 by rho g plus v2 square by 2g plus z2, then the summation will remain same. That is sum of pressure head plus velocity head plus datum head remains constant throughout the flow field. Now we'll discuss what those heads are, maybe just a few slides later. Now that equation was for ideal fluid. What happens if we deal with real fluid? That means in real fluid there will be some frictional forces. So if those frictional forces are there, then whatever is the total energy here in section 1, total energy means summation of all these other forms of energy, pressure energy, kinetic energy, and datum energy or potential energy. So as it reaches this point, some energy will be lost because it has to overcome the friction. If we do not consider friction, then it will remain same, and therefore some losses will occur. So if we measure p2 by rho g plus v square by 2g plus z2, that will be actually slightly less than this p1 by rho g plus v1 square by 2g plus z1, and therefore we have to account for losses occurring in this process when fluid flows from this point to this point, and those losses are mostly because of friction. Now let's try to understand what this equation really means. I mentioned pressure head, velocity head, and datum head, but what they really mean. So this is the equation. Now if you look at the equation, then dimension of each term is that of length when you write the dimensional formulas m, l, t and so on. So if you find out the dimensional formula, all of them has the dimension of length. So they represent a head, which is a representation of energy, some kind of energy. For example, P by rho g is called pressure head, V square by 2g is called velocity head or kinetic head, and Z is called datum head or potential head. So dimensionally, if you want to represent energy with length, then we can, in certain way, we can say that head is energy per unit weight. For example, pressure energy, suppose. So pressure energy is pressure into area, that is pressure force, that multiplied by some length dimension will give you work done or the energy. Now, if you want to express that pressure energy in terms of pressure head, then what you can do is pressure energy divided by weight equals pressure multiplied by area multiplied by length divided by, this term is the weight, which is area into length will give you the volume, multiplied by rho g is the weight. So therefore dimensionally we can say that pressure energy divided by weight or pressure energy per unit weight is P by rho g, which we have named as pressure head. Similarly, you can prove that kinetic energy is mv square by 2 or half mv square. So kinetic head will be kinetic energy divided by the weight, that is this divided by mg. So simply this is v square by 2g. And datum energy or potential energy is mg into z divided by mg. So that is simply the height or z. Now why are they called head? So they represent a height to which the fluid can be lifted with the corresponding amount of energy. If the pressure energy is a certain amount, with that much energy you can increase you can lift a unit weight of that fluid up to a given amount of height. So that height is called the head. So in different languages you can give different explanations of why it is called head. So there are two explanations right here. They represent the height to which the fluid can be lifted with the corresponding amount of energy, or they represent the height of fluid that can store the corresponding amount of energy. So let's try to understand it with the examples properly. So P, the pressure is, as we know, is given by h rho g, where h is the height of a liquid or fluid column. Therefore, this h, it can be given as P by rho g. Let's simply shifting terms from one side to the other side of the equation. So therefore, this head is the height of the liquid column, which will give P amount of pressure. Similarly, in kinetic head, if a liquid is shot upwards, suppose you're taking a pipe and you're trying to see how high the liquid goes after it leaves the pipe, then that will depend on how high the liquid will go, will depend on the velocity. If the velocity is v, then it will reach a height h, and that height h is called the velocity head. So let's try to understand with some kinematics formula. That is, if you remember the old equations of kinematics that you learned in physics, so v final squared is equal to v initial squared plus twice as. Or if you maybe you have remembered this as v square is equal to u square plus twice as, where v is final velocity and u is initial velocity. In this case, that is in case of this fluid shot upward at a velocity v, here the initial velocity is v, the final velocity at the height, at the top of the jet will be 0, that is where it has stopped, and h is that height. So we can write it in this form. Now we simply arrange the equation and we get that this h is equal to v square by 2g. So this v square by 2g is the second term in case of the Bernoullis equation, which we have termed as the velocity head. Simply, datum head is very simple. It is just the height of a point where you are measuring the potential energy. So that's how we can explain the Bernoullis equation and its different terms. So in the next lecture, we'll discuss about some applications of Bernoullis theorem. Thank you.